everyone. Welcome back another video of electronic device. Today we are going to discuss about some application of BJT. Basically, the BJT is used as a switch in many places in the circuit. Okay, it's simply act as a switch. So we know what is the meaning of switch. Switch having two mode of operation. One is on state of the switch and other one is off state of the switch. So take one simple diagram of switch, something like this. Okay, so just something like this. We are giving input to the switch and we are going to read output from here, isn't it? So this is actually off state. The switch is open or switch is closed, switch is off. Okay, so if I close this switch over here, if I close the switch like this, so we'll get a closed one. So whatever you give the input, you can read at the output side. So this is actually the meaning of switch. The same application I can do using the BJT also. So how do we do that? Let's see here. In a switching operation, a transistor is usually controlled in two conduction state, which can be referred to as the on state and the off state. Okay, so look at this diagram. Using this diagram, we are going to explain everything about switching. So look at this diagram. This is emitter and base and collector. Emitter, base and collector. Here you can see this emitter is common for base and collector. What does it mean common? The emitter is connected to base, you can see through a some source, and the emitter is again connected to collector through source and the resistor. Resistor value is 5K and the voltage value is 40 volt, and here also you can see one small resistor, not small resistor, compared to 5K it's bigger, 100K resistance. Okay. So, PNP transistor, we know emitter P plus, N base lightly doped, and P is collector is moderately doped. And here we need to explain the switching operation, right? That means on state and off state of BJT. So here I have given a pulse, okay, voltage pulse. It has got minus 10 volt as well as 10 volt. Peak to peak. Okay, so minus 10 plus 10 peak to peak. So in this region, what will happen if I give a positive voltage to the base? Let's see what is the behavior of Pn junction PNP BJT, and if we give a negative pulse to the base, how does this BJT behave? This is what we are going to see here. Okay, so what exactly I am doing? I am controlling the IC. What is IC? IE is almost equal to IC. We know that this current control from emitter to collector. I am controlling the current flowing from emitter to collector. I am controlling using IB. Okay, so here I am changing the input. Depends on the time. Sometime I give a negative input. Sometime I give a positive input. Okay, so what exactly I am saying? Finally, the collector current IC is controlled by base current. Okay, so that we know that a normal active mode, we know inverted mode that we have seen, and I am going to introduce two more things to you, that is a saturation and a cutoff of BJT. Let's see here. Look at this small diagram. You can see this is in x-axis I represent the voltage between base and collector. In y-axis I have taken voltage between base and emitter. That means base and emitter VBE, here VBE, and here it is VCB, collector and base. Two junction voltage I have taken. So look at this. If both junctions are forward bias, in both VCB and VEB, both the junctions are forward bias, then we call it as saturation, that BJT working under saturation mode. Okay, and see here VCB, the collector junction is reverse biased. This VEB, emitter junction, is forward biased. We already learned that BJT is working normal active mode. Okay, and another one, if both junctions are reverse biased, we call it as BJT is working in cutoff region or cutoff mode. And last one, if emitter junction is reverse biased and collector junction is forward biased, this is also we have seen in previous classes, that is known as inverted mode. So what is the biasing condition for achieving cutoff? Both junctions supposed to be reverse biased. Okay, what is the biasing status for achieving saturation? Okay, both should be forward biased. And look at this diagram. In this diagram you can see negative polarity of battery connected to P, and this is positive polarity connected to N. So this junction is reverse biased. So this junction is forward biased because the negative polarity connected to P type material and positive polarity of the source connected to N type material. So this junction is forward biased now. So now this is in active working in active mode. Okay, so let's see how does it work in cut off state and saturation state. Okay, so initially both junctions are reverse biased. Let's approximate the excess hole concentration at the edge of reversed bias emitter and collector junction. Look at this equation, we know this equation already. Okay, delta PE, excess hole concentration in the emitter junction, this is excess hole concentration at the collector junction. Okay, we know these expressions, these two expressions we know already. From this expression we can write this one. Okay, and here we supposed to give a minus VB value. Here we supposed to apply minus VCB value. What does it mean? I am applying a negative pulse to the base. Now what is going on to the base? A negative pulse is going to the base. So negative pulse always make this junction reverse bias. Now these both junctions are in reverse bias. Okay, so negative voltage is going to the base. So the both junction, this is already reverse bias. Okay, so once the negative pulse is going to the base, this junction also going to be reverse bias, and in that case this term become anyway we can omit this term. So what we will get, delta PE by Pn is equal to delta PC by Pn, almost equal to minus 1. Okay, since we apply a negative pulse to the VB as well as negative voltage to the VCB, we can omit this term, we will getting finally this. So what I can write, delta PE is equal to minus Pn, delta PC is equal to minus Pn. If I draw the diagram, this is a change of concentration change of excess hole in the base region. This diagram you may be remembering, this is a base region, and here you can't see any excess hole because that is a negative value, even less than the 0. So both the junctions are reverse bias. Okay, now let's see, we know the Ebers-Moll equation. I have taken the same Ebers-Moll equation here. Okay, then I am going to number this. This is equation number 1, this is my equation number 1, this is my equation number 2. These two equations are Ebers-Moll equation, and this equation we just see before. And another equality we should take for mathematical simplification, alpha I CS. What is CS? We know it's a collector saturation current. what is emitter saturation current. These are the amplification factor alpha I and alpha n. Alpha n means the natural normal condition and I is the inverted condition. So let's consider these four equations first and take the first equation, that is equation number 1, and we are substituting equation number 4 into equation number 1. What I do here, I am going to substitute for this expression by this. Okay. So what is my expression right now? Because that is equal, right? So I can do that. IES equal to emitter current is equal to emitter saturation current into delta PE by Pn minus I substituted alpha I into ICS with alpha n into IES using equation number 4, and I got this. And look at this expression here, IES divided by Pn is common. I am going to take that is outside. Okay, if I take that is outside, I will be getting like this. Okay, IE is equal to IES by Pn into delta PE minus alpha n into delta PC. And look at this expression, and I am going to use equation number 3 here. What equation number 3 says, P delta PE is equal to delta PC equal to minus Pn. So I am going to substitute for this delta PE and the delta PE with a minus Pn. So if that is the case, I will be getting like this. Okay, emitter current is equal to IES by Pn into minus Pn plus alpha n Pn, and here you can see the Pn is common for all expression. I can take outside. Okay, I can take outside, so I will be getting like this. If I take outside, this Pn and Pn will cancel. Okay, this Pn and Pn will cancel each other. I will get only this, and I will rearrange this expression like this. Okay, IE emitter current is equal to minus IES into 1 minus alpha n. It depends on emitter current is only depends on emitter saturation current and the amplification factor in the normal mode. Current amplification factor in the normal mode. So this will be the first equation. No, equation number 5. And take next equation. I am going to take the equation number 2 and replace alpha n IES with alpha I ICS. So I got this expression like this. IC is equal to alpha I ICS into delta PE by Pn minus ICS into delta PC by Pn, and we repeat the same procedure what we have followed before, and here ICS into Pn is common. I will take outside. Then using expression number 3, equation number 3, I am gonna substitute for delta PE and delta PC, that is nothing but minus Pn, and if I take a minus Pn outside and cancel with the Pn, I will be getting like this. Okay, IC is only depend on collector saturation current with the current amplification factor when it is reverse mode, inverted mode. Okay, and using these two expression, now I have equation for IC and IE, and using these two I can find out expression for IB also. Okay, if that is the case, look at this expression. I can draw a diagram like this for cutoff state of BJT, and this is a emitter, collector and base. Collector current is following upward, and we know emitter current is entering into the BJT. IB is flowing outward from the BJT, and look at this expression. IE is nothing but a dependent current source. It depends on the emitter saturation current. So IE is actually it is entering into the BJT, but this we got it minus, so we have to draw opposite direction. So that is why we have current direction opposite that, IE represented here. Okay, and IC is normal way, it's going up in line with our conventional expression IC, and the IB is flowing outward. Okay, so I can write expression for IB also. What is expression for IB here? So IB can be represented as very IE minus IC. We have a IE expression, we have IC expression. Subtract each other, we will get a IB. That will be the current flowing through this direction. No current is flowing through this BJT. Okay, so whatever the voltage applied at this point going to drop across the BJT. Okay, almost 0 voltage will be across the 5K resistor. Almost this is literally opened. So whatever you apply will be you can read across the BJT. That means if you connect a voltmeter these 2 point, and if you measure between these 2 points, you can read a 40 volt across the BJT. That is actually meaning of BJT in cutoff state. Moving to next one, BJT in saturation. Okay, so right now I have applied a negative pulse. That's what I have explained initially, minus 10 volt and plus 10 volt. When positive pulse comes, how does it behave? That is what we are going to check next. So this region is reverse bias when we applied a negative voltage, but this is already reverse bias because of this 40 volt. Okay, already reverse bias. When I apply a positive pulse to this base, automatically this junction, emitter junction, going to be forward bias. The moment we apply the positive pulse, the reverse biasing state slowly come back and it become forward bias condition. And see, the saturation rhythm begins when the reverse biasing across the collector junction is reduced to 0, and it continues as the collector become forward bias. Okay, but what we required, both the junctions should be forward bias. Okay, the moment I apply a positive pulse to the base, so this will be positive, here will get positive, and here is already negative, so automatically this will be negative. So this junction will be forward bias, but that reverse biasing status should reduce and reduce again at one particular time. There will not be any biasing, reverse biasing completely becomes 0. Then again we go forward. What we can see, the junction, the emitter junction going to be forward bias. Okay, more forward bias and maximum forward bias. This is how it happens. Okay, so when we apply the positive voltage here to the N region, what will slowly the holes going to accumulate in the base, because we applied a positive voltage. Okay, so once holes going to accumulate here, the reverse biasing is going to reduce. That's what I am taking here, the one diagram. The VCB is 0. VCB is actually the voltage between collector and base. So right now this is in reverse bias. That means less than 0, negative actually. Okay, less than 0. Then that reverse biasing is slowly reduced and become 0. That means the VCB is equal to 0. At VCB is equal to 0, the excess hole concentration is almost 0. But what is the case of excess hole concentration at emitter junction? Okay, excess hole concentration, because this is forward biased. Once this become forward biased, we know it start slowly giving holes to the N region. Okay, so the excess hole concentration represented here when VB is positive. What does it mean? When this pulse, positive pulse, connected to the base, okay, the emitter junction going to be forward bias. The forward biased PN junction, we know it slowly holes start moving towards the collector region. Okay, so once the hole this start moving to the negative region, I mean the N region, this is how the excess hole concentration represents. Okay, and now VCB is going to be positive. Assume VCB is going to be slowly increase this concentration. Excess hole concentration is increased from here to here. Definitely the excess hole concentration at the collector region also increased like this, as the area under the curve basically gives the excess hole concentration in the base region in over saturation mode. If I increase this base again and again, base voltage and again, so more number of holes is going to diffuse from emitter to base. So excess hole concentration will become more and more in the base region. That is what this represent here. And now the device is saturated when PC is equal to 0. And the forward bias of the collector junction leads to positive delta PC, driving the device further into saturation. So how do we make that the collector junction is saturated? By increasing the current IB. Since the emitter junction is forward bias and the collector junction has 0 bias, a very little voltage drop appear across the device from the collector to emitter. Here we are applying a positive pulse to the base. Okay, before both junctions are reverse bias because of the negative pulse. Okay, the moment I apply a positive pulse, this becomes forward bias, no doubt. Okay, so holes are injecting continuously. Okay. So the hole concentration become large in the collector junction. If I keep on increasing the base current, the collector excess hole concentration at the collector junction going to be 0. Before it is less than 0 because because this is reverse bias, so excess hole concentration at the collector is less than 0 because of reverse bias. So if I keep increasing the base current, okay, more number of holes getting accumulated here, that slowly bring the excess hole concentration at the collector junction is become 0. Before that would be like this. Is a negative value. So before entire drop across the BJT, right? Once this junction is turned on, become forward bias, become saturated, and this junction also forward bias because of the positive IB pulse applied over here. So current start flowing through this BJT, and the drop become very negligible, and you can read the entire voltage across this 5K resistor. That means this is completely turned on, then you cannot read any voltage across the BJT, and entire voltage you can read across this small resistance. Okay, the magnitude of VCE is, that means VCE is the collector emitter voltage. VCE, it's a very negligible value, very small value, so it is completely turned on. The almost all the battery voltage appear across the resistor. That is what the behavior of BJT when we apply a positive pulse to the base. So when we apply a positive pulse to the base, the emitter junction going to be forward bias. Okay, So then excess hole concentration at the collector junction become 0. Okay. The moment it becomes 0, that junction is going to be forward biased slowly. This is the behavior of BJT when both the junctions are forward biased. Okay. So when we apply a positive pulse, the emitter junction going to be forward biased. So immediately what will happen, hole start moving or diffusing towards the base region. The excess hole concentration become more here, and near to the collector you can see a 0 excess hole concentration. Before it was less than 0 because of the reverse biasing condition, huge reverse biasing condition. Now the reverse biasing condition is going to be reduce and reduce and reduce, become 0 at the particular point. The excess hole concentration becomes 0. That time itself we can say that the junction is saturated, and again more holes are concentrating towards the emitter junction. We can say it's a more saturated or oversaturated junction. So both junction will be saturated, and you can read a current externally. And what will happen that time, that before the drop, entire battery voltage is going to drop across the BJT. Now this drop is very negligible, and the drop will be across the 5K resistor. Okay. So that's about the BJT on and off state. Okay. Thank you.